Hello, everyone. We want to do another another vector problem, but this time we want to discuss force vector. We have a sign here. It's a store sign, and it says, "Come on in. We are open." And this sign that is hanging from a cable has a mass of 60 kilograms. And there are two cables, one on the left, one on the right, that are um, holding this sign up, and there are um, two pivots at the top, and the cables are attached to the ceiling, and the cables are making the same angle of 40 degrees. So it is very clear that there is a symmetry involved in the problem. So by just looking at the question, we can simply say that whatever tension force the first cable on the right has, it must have the same amount of tension force in the left side cable as well. We want to find the amount of tension force in each cable. So first of all, we see that there's no motion here happening. So we are using a very famous formula in statics, which states sigma F equals 0, which means that the sum or the resultant of all forces acting on an object is equal to 0 if the object is stationary, not moving. And of course, if the object is moving but with a constant velocity, still the same rule would apply. In fact, speaking of dynamics, this formula is the very famous formula coming from the second law of motion, Newton's second law of motion. Sigma F, or the sum of the forces resultant of all the forces acting on an object, is equal to the mass times acceleration. And if the acceleration is 0, it means that there is no motion, or it means that if there is motion, the motion is uniform motion with a constant velocity. In either case, the acceleration is 0. And if that becomes 0, so sigma F left side will equal to 0. So here, this sign hanging from the ceiling through the cables is not going anywhere. It doesn't have any acceleration. We don't have any motion. So we know that the right side is 0. The first equation comes from statics. It's a branch of physics that discusses the stationary status of different objects. And the second one is dynamics. And dynamics is when there is motion, there is acceleration actually, there is changing velocity. But in this case, we don't have that scenario. Okay, so we are considering this sign, and we start thinking of what kind of forces are being applied on this object. Obviously, force of gravity is pulling this sign downwards, and that has to be taken into account. But force of gravity is always equal to mass times g. And g is the gravitational acceleration of planet Earth, which it is 9.81 Newton per kilogram. Or you can say 9.81 meters per second squared, because the unit of measurement meters per second squared is equivalent with the unit of measurement Newton per kilogram. And whatever the mass is, in this case it's 60 kilograms, so you multiply 60 by 9.81, and whatever the answer is, that becomes the force of gravity of this object, or in other words, the weight of the object, 588.6 newtons. And because it's force, it's measured in newtons, obviously, force of gravity. So this is the amount of force that pulls this object downwards. And I will draw some vector representing that. So this is the force of gravity, F sub g, and it pulls the object downwards. And then we have this tension force, which sort of holds it on the right-hand side of the figure. So if I add that tension force, with this force of gravity, I should draw a vector which looks like this, and it makes an angle of 40 degrees with the horizontal. This would be, I would say, F sub T1, which means the tension force 1 on cable number 1. This is a cable here, that's cable 1, and this is cable 2, let's say. This is the force along the cable. It makes an angle of 40 degrees, and it wants to pull the object to the right, but it can't because of the equilibrium in the system, because sigma f is equal to 0. And this is the sum of the two vectors, but there is another force, and that's the tension force of the second cable. So I have to add that up as well. So using the tail-to-tip method, or tip-to-tail method, I'm going to draw the tension force of the second cable from the tip of this recent vector. It's going to be a vector like this, makes an angle of 40 degrees with the horizontal. It could be not 40 in some scenarios. It could be like 45 and like 35 or something else. But in this case, in this example, they're both the same angle. But if they're not the same angle, no big deal. This angle would be just a little bit more or less. So now this vector that I'm drawing has to be drawn in a way that it has to exactly pass through the tail of the force of gravity. Why? Because the sum of these vectors, the sum of these three vectors, must eventually be equal to 0. So this means that we will definitely, certainly, for sure, end up with a perfect triangle if sigma f is equal to 0, if equilibrium does exist. These three vectors must add up to 0 vector. So if I connect the tail of the first vector to the tip of the last vector, I should end up with the 0 vector basically. And that's the situation here. I've labeled this other one tension force for the second cable. And according to the Z pattern alternate angles, this angle would be 40 degrees too. So the total is 80 degrees, I say. If that is 40, this has to be 60 degrees. So this is 60, and this is like 80. So 80 plus 60 is 140. So that would leave us with another angle here, which has to be, how much should it be? Oh, this is not 60, sorry, this is 50, because they have to add up to 90 degrees. So 50 plus 40 is 90. This is 40, so that other angle will be 40. This has to be 50. So 50, 50, 100. And this is 80. They add up to 180 degrees. Everything is fine. And now we have a triangle. We have to use our knowledge of sine law to solve this triangle, basically. So it's a triangle like this, apparently. This angle is 80 degrees. This one is like 50 at the top. This one is 588.6 newtons. And this one is force tension sub 2, force tension sub 1. And we want to find those two. So apparently there is a diagram like this. So I can still draw the arrows, not a big deal. All right, so how do you solve this? Well, we use sine law, obviously. So we're going to say force of gravity divided by sine of the angle 80 degrees, the opposite angle, equals tension force in cable 1 is this divided by the sine of the opposite angle, which is 50 degrees. Okay, and that is equal to tension force in cable number 2, which is this side, divided by the sine of the opposite angle, which is 50 degrees. We said it before. Okay, so these two fractions are the same. The tension forces are the same. We have absolute symmetry involved in the problem. We're not surprised about this. So from here, we can say Ft1 is equal to force of gravity 588.6 times sine of 50 divided by sine of 80 degrees. So doing the cross multiplication, and we just need a calculator. to figure this out to see how much the answer will be. So we're going to go 588.6 times the sine of 50-degree angle, and we're going to divide this by sine of 80 degrees. You can use your calculator to figure out how much this is going to be. 457.8. Okay, 457.8 is what I got. 457.8. The unit of measurement is newtons. This is the tension force in the first cable, and it happens to be the tension force in the second cable as well, right? Because of the symmetry involved, because the triangle is actually an isosceles triangle, because the length of the cables are the same, because of the symmetry involved. Okay, but if the angles were different, one was 30, one was like 50 or something else, then the amount of tension force in each cable would be different. One would be stretched more than the other, let's say. The tension force in one cable would be different from the tension force in the other one, but in this case, they're both the same. It's a word problem at the end of the day, so we need to write a final closing statement. We're going to say the magnitude of the tension force in each cable equals 457.8 newtons, and that will be your paraphrase for the problem. Okay, so this was just an example of a force problem I wanted to share with you, and everything starts from the formula that comes from statics. The resultant of all the forces acting on the object is equal to 0 because there is no motion involved. Acceleration is 0. And the sum of all the forces acting on the object, including force of gravity, tension force, or any other forces, the sum of all those forces must equal to 0. Okay, I hope you understood how this question was done. There are similar questions in the textbook you can try. Thank you.